Okay, I believe we can start now. So, Assalamualaikum warahmatullahi wabarakatuh, and very good afternoon to all participants, and of course, very good morning to Professor Arend Schwab. So, welcome everyone. So, thank you for joining us for today's webinar. So, my name is Muhammad Ezral Baharudin, and I'm your host for today's event, and I'm researcher at Universiti Malaysia Perlis, also known as a UNIMAP. So to those who didn't know about UNIMAP, to cut a long story short, UNIMAP is one of the technical universities in Malaysia, which is located at the northern part of Malaysia. So today we are presenting a webinar with the title of Bicycle Dynamics and Control, How We Solve the Mystery, which will be presented by our Professor Emeritus, Arend Schwab from TU Delft, Netherlands. So just a little housekeeping before we get started. If you have any questions during the presentation, for example, during the presentation, so please type them into the question box in your Google Meet chat box, and I will try to compile it and then bring them during the presentation, or actually we also have time at the end of the presentation, this Q&A session at the end of the presentation. So another things, if you experience any technical issue regarding today's webinar, your audio, for example, the visual is not so good looking, so maybe you can just write it into our chat box, and we will try to solve it for you. So now, without further ado, so we will turn the time over to Professor Emeritus Arend Schwab. So our presenter today is a Professor Emeritus at TU Delft. His expertise cover multi-body dynamics, biomechanics, bicycle dynamics and control, sport engineering, speed skating, robotic, and legged locomotion. So just name it, all its dynamic aspect he can cover with that. So Professor Arend's interest in bicycle dynamics was first ignited by Andy Ruina during the sabbatical session in year 2002 and 2003 at the Cornell University, United States. So this interest led him to the creation of TU Delft Bicycle Lab, which Professor Arend founded in the if I'm not mistaken, in mid-2000, and then ran it until his retirement day in year 2020. So I believe, Professor Arend, the floor is yours, please.
Ethel, thank you very much for this nice introduction, and also thank you for giving me the floor to present the work we did at TU Delft on this topic of bicycle dynamics and control. As already said, I'm emeritus now with all professors, I think, from university. I'm still very busy in the field, although I also enjoy some more free time. As I said, it's stated here in biomechanical engineering, but actually my background is theoretical and applied mechanics. But well, you need an application for that, and bicycle dynamics and control seems to be an interesting one. And I hope to get your interest also during this talk for the topic. Okay, so let's start with a motto, and the motto actually for this presentation is that everyone knows how a bicycle is constructed, right? I mean, it's two wheels and a steering assembly, and that's it. Yet nobody fully understands, and with the nobody, I also include myself. Although I've spent more than 20 years now working on the topic, I'm in fully understanding how it works. That's tricky. I couldn't have done this work by myself, of course. That's the nice thing of academia. You work together with all kinds of people. At TU Delft, of course, a whole list, but also at Cornell University. That's where the whole research started during a sabbatical year in 2000. And then UC Davis, and actually among the world everywhere, where there are researchers interested in bicycle dynamics. There are two key papers actually on this topic from our group. And the first one is on the linearized dynamics equation of bicycle and steer, a benchmark paper. That's with the Proceedings of the Royal Society. And that's the journal, in which Isaac Newton published. So we're among good friends, I think, there. And the other one is in Science, where we say a bicycle can be self-stable without gyroscope and caster effect. And we actually needed that Science publication very hard, because before the science publication, everybody was saying, bicycle dynamics. I mean, bicycles are more than 100 years old. What's new? Go into nanoscience or whatever. I hope to show you that there are new things now. Let's start with an observation. This is a movie, Jour de Fête, from Jacques Tati. It's a French movie. It's about a postman who wants to rationalize things, and by rationalizing, he wants to use a bicycle. And you see a bicycle move by itself, and of course, everybody thought, well, this is a trick, right? This is movies. Everything is a trick. But actually, almost every bicycle can do this. If you just give it a certain speed, you let it go, it stays upright. It can even go around a corner, as you see, by itself. You need some. Here is a bike, random bike in a car park. We propel it forward, it stays upright. So highly unstable at 0 speed. Given some forward speed, the bike seems to stay upright by itself. Now, we call this stable, but I would say bikes are what you would say super stable. You can hit it sideways, it starts oscillating, but the oscillation dies out. Now, mechanical engineers immediately think, oh, a dying oscillation, that has to do with damping and friction and those kind of things, dissipation of energy. But there is not so much dissipation of energy here in this lateral motion of the bike. I mean, there's not much friction in all the parts. And so the big question is, of course, where does this asymptotic stability come from? Well, the question is, of course, already very old. Here you see a picture on the evolution of the bicycle, where it started around 1890 with the hobby horse, where you propel it with your feet. And then people want to go faster. And what do? They mount pedals on the front wheel. And then instead of pedaling with their feet on the ground, they can propel the front wheel. But they want to go faster still. And what do? The front wheel becomes bigger and bigger. And again, this gene which people have, everybody has this part of the gene, and it says faster. Then there's some limit, and it has to do, of course, with the leg length of the person, right? And then you see a jump in the evolution. You see that there comes a chain drive with a gear ratio, but you see clearly this is an evolutionary thing, because the front wheel is still this large wheel. Then people, of course, say, hey, this is crazy. We don't need this large wheel. And then again, you see to show that you don't need a large wheel, a very small wheel. And then finally, we end up in 1899 with the current safety bicycle. 2 equal-sized wheels, chain drive, and pneumatic tires. And if you look outside, and most of you maybe, some of you maybe came to work today, on this contraption, I mean, your bike nowadays is not so much different from this machine. Well, at that time, 1890, around that time, also scientists started to wonder, of course, about this stability. And both in the UK, Whipple, as in France, Carvalho, worked on models. And in this period, actually, of Einstein, you say, we want a model as simple as possible, but not too simple. So we do a lot of assumptions to get down to the core of the problem. So we assume rigid bodies, everything fixed to the rider, no control, everything is symmetric, idealized contact. So we have point contact and no side slip, we level road, no frictional propulsion. And then when you think of that system, you end up with a bike which can move back and forth. That's 1 degree of freedom. Then it can tilt left and right. That's a second one. And then, of course, you can steer with your steering assembly, and that's a third one. So you have 3 degrees of freedom in this system. And the big question is, of course, what is the dynamic behavior? To investigate this forward motion and to look at the stability, you write down the equations of motion, which is just, I mean, this looks complicated, but it's just mass times acceleration is forces. Now we wrote the forces on the other side of the equation, and we made linearized equations because we want to investigate stability. So we look at small motions of the lateral motions, the roll, the phi, and the steering motions, delta, and of course the forward speed, v. Now for straight ahead motion, for small changes, the lateral motions, so the phi and the delta, the rolling and the steering, is decoupled from the forward speed, meaning that forward speed is approximately constant. And for the lateral motions, we have 2 degrees of freedom, roll, and steer. And with those 2 degrees of freedom, we can investigate stability of the motion. For that, we write linearized equations, we linearize them, we put exponential motions, assume exponential motions. We write characteristic equations. It's 2 second-order equations. We have 4 roots for this equation. And these 4 roots are a function of all the parameters. Now, we find, of course, this forward speed an interesting one, because at 0 speed, the thing just bang falls over, and given some forward speed, the thing stays upright. So forward speed is an important one. So we plot then these eigenvalues of the characteristic equation as a function of the forward speed. So here we see the eigenvalues. Now, in blue, we have the real part of the eigenvalues, and in red, we have the imaginary part. The blue part determines if it's stable or unstable. So unstable is a positive one, stable is a negative one. And the red one, the imaginary part, is, of course, the oscillating one. So we see at 0 speed, that's around here, we have 4 roots, and they are equal and opposite, like a double inverted pendulum, because the thing is not moving. And then at some forward speed here, around this speed, 2 roots coalesce, and we find a complex conjugated pair, meaning an oscillation start. And that's the motion we saw, that this roll motion is oscillating. Then, of course, it's still unstable, this motion, and then at a certain speed it becomes stable. And actually, after a certain speed, all motions are stable. So this very simple model already explains that a bicycle can be self-stable from a certain speed on. Now, to show that it's not about real small motions, we make a full nonlinear model. We simulate it in a computer. At low speed, you hit it, it starts oscillating, and you crash. And this is actually exactly what happens when you learn how to ride a bike, because you think it's dangerous, you go slow, and when you are slow, you're unstable, and you start swerving, and then you fall over. Now we go from this unstable region, we go to the stable forward speed region. Then we do the experiment again. So, and we hit it sideways, and then you see this oscillating thing, and you see the oscillation dies out. So, yes, even the full nonlinear model of this 3 degree of freedom model for a bicycle already shows this stability behavior. Okay, remains the big question, of course, this bicycle stability, self-stability. Where does that come from? Now, I always call it some auto magic control. This whole self-stability. So the big question is, how can the bike stabilize itself? And actually, that's a very tricky question. So let's go back to our own world and say, hey, how do we balance a bike? Because at slow speed, the thing is unstable, so we have to do something. So then you have to think, what am I doing? Well, actually, that's also a tricky question, because you have no clue. You are moving with your upper body, you are steering, and it's not completely clear what you are doing. So we go back to one easier problem even, and that's, how do we balance an inverted pendulum on our open hand? So this is our hand, and here we have this inverted pendulum. And then the thing is, of course, if it falls to the left, you quickly move your hand to the left to move the support. And if it falls to the right, you quickly move your hand to get the support under the center of mass. So that's the way how you balance a stick on your open hands. Now, in the same way, a bicycle is like a stick, and the hand is the world. So you would say, oh, then I have to move the world to balance a bike. That's a bit tricky to move the world. But what you have in a bicycle is you have a steering assembly. And if the bike has some forward speed and you operate the steering assembly, then you are able to move the contact points laterally. If you move forward and you steer to the left, then you can move your contact point to the left. So by steering, you can move your contact points. Now, bear with me. If you fall to the left, you have to move your contact points to the left, meaning you have to steer to the left. So the moment you fall to the left, to balance, you have to steer to the left too. And that sounds very strange, of course. And most people actually, when they start learning how to ride a bike, they fall to the left and they immediately start turning to the right, which has a very dramatic effect, because they will fall even more. And this is also maybe the reason why you cannot ride a bike immediately when you buy a bike in the shop and you say, okay, how do I balance? Steer to the left or fall to the left? Oh yeah, that's easy, I can do that. No, it's an acquired skill. It's something you have to learn by doing. Small anecdote. Does that really work? We have students who do projects. In those days, Lego Mindstorms was very popular and they built walking robots with it. But Joep Mutsaers from TU Delft, he was an avid motorcycle rider. And he said, well, instead of building a boring robot as out of the box, I'm going to build a motorcycle. So Lego Mindstorms is Legos, of course. Then you have motors and sensors and a computer. So you have a steering motor, you have a propelling motor, you have a sensor which senses that the thing is falling over, and you have a computer which can, well, control some things. And in this case, it will control the steering based on the sensor of this and based on the forward speed. Now, Joep was a motorcycle rider, and he said, well, I can do that, that's easy. But he couldn't get the thing working. Whatever control program he put in, it didn't work. And he was in a hurry to go to his internship in Switzerland, and people said, well, actually, in the back there's the bike lab and there's Professor Schwab, and maybe he can help you. Well, Joep came in and I said, well, yeah, sounds like a doable job. Let me see, you have a steering motor. It's a DC motor, right? Direct current. So the amount of voltage means a certain torque. You have a lean rate sensor. Well, you have to steer into the lean. So let's apply a voltage which is proportional to this lean rate, and let's do it 10 times of 100 or minus 10 or minus 100. You have to fill a little bit with a feedback gain and the signs, and that should work. And then Joep looked at me in the face and he said nothing. He just looked at me. I said, yes, Joep, what's wrong? He said, well, it's only one line of code in my controller. I said, yeah, okay. And then, well, Joep went away. And I think after 4 minutes, he came back with this video. And this is clearly a demonstration that to balance, you have to steer into the undesired fall. It works. The thing is self-stable, right? Actually, if you look at the slow motion video of a real bike, you see it falls and then it steers into that fall. It falls and then it steers into that fall, meaning you see this steering into the fall as a stabilizing motion, stabilizing mechanism, clearly also in a real bike. Remains, of course, the question, why does it steer into the fall? So why does it steer in the right direction and at the right time, the right amount? Actually, there are two groups in this whole explaining this self-stability. And it's like in real life, with the screeches and the sneeches, or with the red and the blue and the left and the right, you always have two opponents. And well, one opponent says it's the gyroscopic effect of the front wheel. So the front wheel is a rotating body, and the rotating body is falling, and then there, about the third axis, there's some torque, and it will stabilize. But actually, there's another group, and they say, well, no, it's not about the gyroscope, it's about the steering geometry, because this effect is very small, and it's that the steering axis hits the ground in front of the contact point. So the contact point is behind the steering axis, and you can compare this to a caster wheel, which is under your desk chair or in your shopping cart. So they say the trail is the most important part. Now, first start with the gyroscope people. Well, this gyroscope explanation already started in around 1910 by two what I call half-gods, Klein and Sommerfeld. Felix Klein, famous mathematician from the Klein bottle, and Arnold Sommerfeld, who was nominated 81 times for the Nobel Prize. They wrote a 4-volume book. I mean, it's about this wide, the 4 volumes on the shelf, on the theory des Kaisers, which means theory of gyroscopes. And of course, when you're in gyroscopes, wherever you look, you see gyroscopes, right? And then they saw a bike and they say, hey, the front wheel, that's your gyroscope. Fritz Noether did most of the problems actually in the book. And then they went into the derivation. They knew their classics, so they used the Whipple-Carvalho paper. They derived the equations, and then they showed that If you kill the gyroscopic effect, then it can never be self-stable. Well, unfortunately, my colleague, Jan Meijert, he went meticulously through the whole calculation of 1910, and he discovered 2 sign errors in the thing. And if you then correct for those 2 sign errors, it's not so obvious anymore that if you kill the gyroscopic effect, that the thing will always be unstable. So that is one of the explanations debunked, actually. Then the other one about the trail being a necessary item, a positive trail being necessary for self-stability. In the 1970s, there was Jones, who was who had a PhD in chemistry from Cambridge, I think, or Oxford. Well, Cambridge or Oxford. And then David Jones was, well, he was mostly interested in why does one bike is far more easy control than the other one. And that actually has, and then he was interested, of course, in self-stability in that sense. So, well, he knew his classics. So he built a bike where you can kill the gyroscopic effect by mounting a counter-rotating wheel next to the wheel, which does not touch the ground, but it kills in that frame the gyroscopic effect. And he said, hey, mommy, I can even ride without hands, no problem. The thing is very stable. Whereas if you started to tinker with the trail, this distance, if you made the trail very large, it was very good rideable without hands. If you made the trail negative, so the contact point is in front of the steering axis, it was horrible to drive, and he could not drive it without hands. He went into a whole derivation of potential energy to show that with a positive trail it's always stable and negative it's always unstable. However, that was based on potential energy, and potential energy in a stationary bike is identical to the potential energy in a moving bike. And if you then correct for the dynamics, if you include that dynamics effect, it's not so obvious anymore that you need a positive trail. Maybe you can also do it with a negative. So both explanations, gyro and trail, are not sufficient to explain why does the bike stay upright. So what do? Well, you go back to your equations again, and then you formulate this stability criteria. Well, the equations, they have 25 bicycle parameters. And these bicycle parameters like wheelbase, trail, head angle, mass distribution, all these 25 parameters, they go into the equation of motion, they go into the characteristic equation of Horowitz, and then the Routh-Horowitz stability criteria tells you that all these coefficients, the A, B, C, and D, have to be positive. And all these A, B, C, they are all functions of these 25 parameters. If you want to find out for what condition that holds, for which parameter combination, you probably can print out all these equations, and you can paint the walls of the whole University in Malaysia with that. It's an exploding thing. So that's undoable for those 25 parameters. So what do? Well, we make it even simpler. We make what we call a 2-mass-skate bike, where you have only 8 parameters. And the 8 parameters are, you have a wheelbase, you have a tilted steer axis, you have a mass and a position of the mass on the rear frame and on the front frame. And as you can see, it has no gyroscopic effect because it's on skates, and it has no trail because the steering axis hits the ground in the contact point. So this is clearly a bicycle with no gyroscopic effect and no trail, and we will show you that the thing can be self-stable. For certain combinations of mass and mass distribution, and those conditions are not so interesting for now, but we can find regions where from a certain speed on the thing is always stable. Of course, that's stable without gyroscope or trail. So it's not a necessary thing to have gyroscope or trail. A thing can be self-stable. However, you would think, well, this is linearized dynamics, and maybe it's only about small numbers. So let's build a prototype and do the experiment. So we built the prototype, you propel it forward, you release it, it stays upright. The next thing is you propel it forward and you hit it sideways. You will see it oscillates a little bit, and then it stays upright. And this is the proof that a bicycle can be self-stable without gyro and without trail. Remains, of course, the question: how does it stay upright? Well, that has to do, of course, with this strange mass distribution, that the mass of the rear frame is high up and the mass of the front frame is lower and in front of the steering axis, meaning that if the thing falls over, that the steering will follow in that falling over. And so the explanation here for the self-stability is it's self-stable because of the mass distribution. But the bottom line is that with these bicycles, with all these 25 parameters, you can play around to get self-stable bicycles in many, many ways. You can play around with a gyroscopic effect, which is helpful, but not necessary. You can play around with a trail, which is helpful, but not necessary. And you can play around with a mass distribution, which is helpful, but again, not necessary. And by playing around, you can make all kinds of contraptions with all kinds of dynamic behavior, stable or unstable. Okay, the next question is, I want to point out that this presentation is very techy and so on, but there are actually after our publications, people on YouTube people in the real outside world got interested, and they started to make these very nice short videos of 10 minutes where they explained and demonstrated in a nice graphical way. On Minute Physics, there's a nice one which shows our work. And the other one is on Veritasium on YouTube. There's also a cool one. I think Ezrael is recording this, so afterwards you can just pick up the link and please look at them. They're very well made, but it's all based on this work, of course. Okay, so yes, the bike can be self-stable from a certain speed. Still, we also ride at slower speed, and we are able to control that thing. And the big question is, of course, how do we control that unstable bike on the one hand? And secondly, why does one bike feel so much different than another bike? If you have a racing bike or you have a mountain bike or a city bike, they in behavior, in control, they all feel different. And how does that come? So the big question is, how do we control the unstable bike? Now here you see two pictures. One of them is of course very famous, and that is my daughter, because I used her as a study object. This, how do you balance and how do you learn how to ride? Now, a short intermezzo, and it's a question. If you ride your bike and you want to turn to the right, what do you do? Now, of course, I used to ask that in the audience, and then I got answers. So I'll just give you a second to think about it. Yeah, you ride straight, you want to go to the right. What do you do? Well, I think that 38 people out of the audience will probably say, well, you steer to the right, of course, because you have to go to the right. Correct? Well, actually, it turns out that to go to the right, you briefly steer to the left, and then you just let go. And that sounds very strange, of course, but if you look at this video of the simulation, I ride, I steer to the left, and bang, the bike falls over. Now let's do that in slow motion. So here again, I move forward, I steer to the left, and what happens, my contact points go to the left, so I fall over to the right. And that's exactly what I need, because to make a right turn, you have to have some lean angle to the right. Now, you cannot push against anything. So how do you get your lean angle to the right? Well, there's only one way, is by moving your contact points to the left. And how do you move your contact points to the left? Well, by steering to the left. So it's a thing we unconsciously all do. And if you say, I don't do that, well, just start riding a bike. Instead of holding on the handlebars with your hands, do it with your open hands, push against the handlebars, push a little bit with your right hand, and you will fall. You will notice, oh, I steer to the right. So then you steer to the left, and you finally get into a right turn. Just do the experiment yourself. It's pretty cool. The question, of course, about steering balance is older. At Delft in the 70s, people were interested in should we prohibit people who are intoxicated by alcohol or drugs to ride a bicycle. Now they wanted to do experiments to see how well do you still behave with intoxicated by alcohol or drugs on a bike, and they couldn't do it on a real bike, so they made a simulator. And you see here a picture of this bicycle simulator from the 70s, and they measured the behavior of the rider. Of course, a lot of people were interested in participating because it was free alcohol and free drugs, right? And that's the Netherlands. And of course, the outcome of the research was, yes, of course, it's dangerous, so you shouldn't do that. So by law, it's forbidden. After that, nothing much happened in bicycles, but on motorcycles, a lot happened because in the US around the 1970s, the Department of Transportation thought, well, there are so many accidents with motorcycles, maybe they are inherently unsafe, these vehicles. And so a large research program, mainly David Weir started it by theoretically looking into the dynamics and control, and then experimentally looking into that. And the conclusion was, no, they're not inherently unsafe. It's okay, but it's a very strange control behavior, which you have to learn, right? Steering to the fall. We were interested in what you are doing, because if you think about the control, you think about, oh, I steer and I lean, and what do you do? So we set up a rider, full human motion capture, riding on a treadmill at various forward speeds and observing the motions. Of course, on the left you see the rider, on the right you see the reconstruction. And the conclusion actually was that if you order the motions of the bicycle and the rider in order, the bike moves, of course, most, but all the control is mainly done by steering. And only at very low speed, some control is done not by upper body, but by moving your knees in and out. And that's this part. So the upper body motions are not control motions. They are just dynamic motions because the bike is moving, and you have two masses and they have to move relative to each other. So the conclusion was then that all control is done by steering. And that is important, because then from a control point of view, you have a system with multiple inputs, but one output being the steering control, right? Okay. All very nice, all these stories about dynamics and stability and parameters and whatever. Very techy, but what is the relevance to society? Well, the relevance to society is that we have emission zero in traffic about death and seriously injured, and for cars we're getting there slowly. But for bicycles we're going up instead of down. So in every year more and more cyclists get killed in traffic and are seriously injured. It has to do also, of course, with exposure, because people are getting older and staying longer on the bike. But if you look in detail, it's 80% are elderly, and they are not hit by a car or a truck. They just fall over. 75% of these accidents are single vehicle accidents, meaning they just fall over with their bike. And of course, the bike stability plays an important role there. The control, the handling, the stability. So that is actually relevant for society. Can we improve that? So we have a various number of projects for that, both in consumer industry as in sports engineering. So in consumer industry, there were questions about safety of regular bikes and e-bikes for elderly. So we compared them in a large test, and we showed that although elderly, they seem to go faster on an e-bike, actually they go as fast as middle-aged people on a normal bike, and it's not unsafe. What is unsafe for elderly is mounting and dismounting and starting and stopping, but not riding. That turned to be was the conclusion. Then in sports engineering, we started with the then giant Alpecin and it's now called Sunweb team. We started by looking at optimal power distribution in a time trial, in an individual time trial, and later on we went on. I will also tell a little bit about team time trial. So those are two application fields. For the stability, we were very interested, can we do safe experiments indoor instead of outdoor? So we were always fantasizing about some bicycle simulator. We made some contraptions. This is a stationary one. We're now busy with a leaning bicycle simulator. The main thing is that you have to have a good haptic feedback on the handlebar. So you need a motor which gives you the right forces, which you feel in cycling. We discovered that the head-mount display is too immersive, actually, so it's better to have screens, but this is an ongoing project. Then again, in the consumer industry, with the e-bikes, we have this step-through frame, and they show this very unstable shimmy behavior. So if you let your hands go of the handlebar, then suddenly you have this high-frequency behavior. Race cyclists, elite cyclists know this also. And we were able to make a design tool so that so designers can build a bike, design them, which is then shimmy-free. On the other hand, for the consumer industry, we say, well, if people cannot stabilize the bike, why don't we let the bike stabilize itself? So we add a torque motor to the steering assembly, and that adds a torque which stabilizes the bike, which makes it easier to control. And actually, you have to do nothing, because it controls itself. And you can compare it a little bit like a lane assist, where the car stays between the lanes. Of course, if you jank on the steering wheel, you will get out of the lane, and that's the same with the bike. But if you just follow the flow, you will just nicely stay upright. We also work on tire mechanics, of course, because the tire is the contact with the ground, very important. With automotive tires, there's a lot known. Professor Pacheca, with the Pacheca tire model, he's from TU Delft. He was one of my mentors. We used some setup there. We made an apparatus to measure camber and cornering stiffness of tires. Then in sports engineering, we started with a single individual time trial to look at power distribution, but we also noticed in the team time trial that originally the skipping was done like the front went to the back, and then the next one stayed for a number of seconds and then went to the back. And then we thought, well, actually, this is a nice optimization problem. You have like 8 different engines, and they all have their specific power, etc., and their specific drag. And then we just optimize for how are we going to do the skipping. And then we ran a lot of optimization programs, and then the outcome was, well, you start in the order 1, 2, 3, 4, and then rider A stays for 12 seconds, then goes to position 4, and rider B starts for 15 seconds. He goes to position 7, and then so we had a whole scheme. And then the Sunweb team said, yeah, that's very nice, but we're not going to do that. Yeah, but this is the optimal solution. They said, this is too complex. We cannot execute this. So we had to tune down a little bit, but I think in the Giro, the Sunweb team was by surprise, the competitors found the Sunweb team very good at the team time trial. So their new skipping behavior were pretty good. We also looked for the sports engineering at descent. So the big question is, why is one descender so much better than another one? And we said, well, let's first observe. So we have a measurement bike. This bike is full of sensors and cameras, and then we can record how a good rider is going downhill, and from that we can give instructions to novel riders with Google Glasses and other things. We can guide them then in what is the ideal line, when to brake, etc. This is still an ongoing project. And then for the Dutch Olympic team, we built a new track bicycle for the Olympic Games in Tokyo. And I want to focus a little bit more on that. A new track bicycle for the Olympic team. Yeah, I think I have 5 minutes for that. That's good. So for the Olympic Games 2020, the team wanted to have a new bicycle. And the bicycle was originally a Koga bicycle, a Koga Miata. This is the original bike. And then the question was, of course, why do you want a new bike? And then they said, well, because we want a new bike. It's totally unclear. Are you not happy with this one? Yeah, but a new one is better. Okay. So then Koga formed very, very wisely a multidisciplinary team with TU Delft for handling and control, Pontus for the engineering, Actiflow for the fluid dynamics, and then we were aiming at Tokyo 2020. So, well, the first thing we did was, of course, we observe. what is going on with the current bike. And if you look closely here, you see that this is not an ideal configuration because your knee is hitting your elbow. So I would say, as a outsider, oh, the bike is too small, right? Or the person is too large, but we cannot change that. The bike is too small. They don't fit the bike. Look at this guy. I mean, this is horrible, right? You don't want this. You have to put a lot of attention and control in not hitting your elbow. So we said, well, why don't we do two things? Well, of course, we make the bike very aerodynamic, but that's easy stuff. That's just doing calculation. But let's look at the rider. Let's take his original position and let's look on an ergometer. Let's put him in an ideal situation where he has more freedom, but still in an ergonomic position and still able to perform enough power. And that's on the right side. And then those are the markers for how the bike should be. So we built a bike around the person. And we did the same things for the ladies, same kind of problem. Of course, the riders had a difficulty in adapting to that new posture. That's with everything. But we said, well, trust me, I'm a doctor, it will work. Then there were some questions about handling and control. So one of the riders said, well, if I ride my bike, my Koga bike, which is on top here, if I ride my bike around the corner and I try to accelerate down between the lines, I have a hard trouble staying between the red and the black line, accelerating in the corner. The control, it's very nervous. However, she said, I also have a Look bicycle, and that's on the bottom, this French one. And in the Look bicycle, sometimes I train with that one, and I do not have that problem there. And then we said, well, it has to do with the dynamic stiffness of your bicycle. Dynamic stiffness meaning what stiffness do you feel at the various forward speeds, and that changes because it's a real dynamic problem. So what did we do? We calculate for those two different bikes the dynamic stiffness as a function of the frequency by which you steer and the forward velocity. And this is the Look, and you see at low speed it has a certain stiffness, and at higher frequency it increases, of course. But this stiffness, and if you look at the original Koga bike, it's very, very low on stiffness in this region. So what we can change, of course, the whole steering assembly. We can do the trail, we can do the head angle, a little bit mass distribution, or where you put your hands, and then we can try to mimic this. So that's what we did. For the new bike, for every rider, first of all, we made it such that they have the ideal position, meaning we have 3 different sizes bikes. We have every cockpit is totally individual, plus that the steering geometry is also adapted to have this certain stiffness at this speed region. The bike was introduced, and of course we as engineers were really sitting like, oh, I hope it works, right? Well, already at the World Championship in Berlin, before the Olympics, there was also a phenomenal world record by one of the Dutch players. So we thought, okay, it's probably gonna work. And then, of course, at the Olympic Games, which were 2020, but they were staged in 21, we had 3 gold medals, 1 silver, and 2 bronze medals. And of course, it's the riders who get the medals, but I think the bike was also helpful in that. I have 20 seconds left, right? And I think this concludes the presentation.
All right.
Okay, I think as we're open for questions.
Yep. So thank you so much, Prof. Arend. So now we already 45 minutes, exactly 45 minutes. Thank you so much, Prof. Arend.
I try and do my best.
Okay, so is there any question? Yeah, we have here. Yeah, we have a Professor Muzamir here, Prof. Arend.
Yeah. Okay. Thanks, Dr. Ezra. Prof, I have one question. Okay, based on the modeling, if the person is slightly big or fat, can we determine the minimum speed of a stable the bike upright, and is it applicable in real life?
So you mean if the person is big or heavy,
Yes, yes, yes.
does that influence the stability? Is that the question?
Yes, yes, correct.
Well, actually, not so much.
Aha.
No, that's not so important, because, well, for bear with me, it's like a stick which is falls over, right? And
Okay.
there's some center of mass, but what is falling over? It's gravity, right? And the mass is also in the gravity term, so it's not so important.
Okay.
It is important when the person is very small, very low. If he is very low to the ground, then it's
Alright.
like a short stick, and a short stick will fall fast, and whereas a long stick will fall slowly. So the higher you are, the slower you fall, and the easier it is actually to control the whole thing. Yeah.
Okay. Okay. Good. Okay, Prof.
Mass
Okay.
is not so important. Yeah, totally.
Yes. Okay, Prof. Second questions. Between which one is the best to teach kid on how to ride a bike? By using a long
Ah,
handlebar or short handlebar?
I love this question. Thank you, Mizan. I love this question. So, how? Yeah, well, let me rephrase it. How do you teach your kid how to ride a bike? Well, first of all, you take a bike, you lower the seat, and you remove the pedals.
Okay.
So they start like this hobby horse thing, like in the old days, right? They just
Yeah.
with their feet they pedal on the ground, and they feel safe because they almost always have one foot on the ground, either left or right.
Yes. Yeah.
And then they learn a bit about the dynamics of the leaning and steering. In that way, they in a natural way they learn this whole dynamic thing. Now,
Yes.
as I said before, every person has this part in his gene which says faster, faster. Yes.
Okay.
So the gene says to the kid faster. So he starts going with his feet faster, but that doesn't work. And then he said, "Oh, Daddy, can I have my pedals, please?" You mount the pedals again on the bike, you raise the seat, and you push him, and he can ride. That's it.
Okay.
He can ride.
Yes. 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 Okay.
Maybe he
Clear, Prof.
crashes 2 or 3 times, but after that he can ride. So I
Okay.
really encourage people to get rid of those trainer wheels or strange bikes, or this is the way to go.
Yes. Thank
So
you.
which
Thank you,
means
Prof. Yeah.
we can conclude that to teach our kids use this kick bike first.
Yeah, kid bike. Yeah, it's now called it's a product, but you don't need to buy the product. Sorry, but you just get a regular your kid's bike with the pedals. Take the pedals. You're an engineer, right? Take the pedals off,
Yes.
lower the seat. That's
Yes.
also a kid bike.
Yes.
Yeah.
So that's all from Zame.
Yes. Yes. That's all
Yes.
from me. Yeah.
Okay.
Thanks.
So I open to others. All right. So I open to others. Is there any question? Maybe Atika, maybe. So is there any question to ask others? So actually I received a few questions actually here.
Yes, sure.
Maybe while waiting for that, I don't know, is it okay or not, but the question that I received it here, someone asking about when you reduce the bicycle parameter from 25 to 8. So how we can know that does it affect the stability accuracy from the modeling purpose?
No, well, that's a good question. There was also our question, of course. Okay, we reduce this number of parameters. We have linearized the equations. Is it
Yeah.
only about small numbers, etc.? So we went into a number of steps. So the first thing was, of course, we built a full nonlinear model of this 2-mass skate bike, of this eight parameter thing. Full nonlinear model that also showed this stability behavior. So then we were confident that it's not about small numbers. It's probably gonna work. And of course, then the next step was just to build the experimental bike, because, well, the proof of the pudding is to eat, right? So build the machine and show that it stays upright. And well, we built that machine, of course, not on real skates, but with counter-rotating wheels to kill the gyroscopic effects and so on. And eventually, with the real machine, we demonstrated, yeah, it works. We even went to the trouble of measuring the motions and then compare it again to the model. And then that's all in the science paper you can see. We show that, yeah, also the dynamic behavior is comparable to what the model predicts. Yeah.
All right. So these two, another two questions came from me actually. So I would like to ask, I would like to ask you during my time there in Finland when we met.
Yeah.
So you show to us your experiment rig, whereas you say that we have one rig without the wheel, if I'm not mistaken. It's like a skate, right?
Yeah.
The video that you showed to us just now. And then if we notice that you put it there, these two wheel attached together, is it the purpose of that one is to counter the gyroscopic effect?
Exactly. It's to kill the gyroscopic effect. So you have one wheel which is rotating in one direction, and the other wheel on top of it is rotating counter, and it's all in the same frame. So then you have an angular momentum in this direction and in this direction, and those two you can add them up because they're in one frame, and you have a zero angular momentum. Yes.
So, and then that experiment is to prove that the bicycles, the stability of bicycle is not caused by the gyroscopic effect. Is it correct?
Yeah, correct. Yeah.
All right.
And we also made the trail zero. We even made it a little bit negative. So the contact point is a little bit in front because in reality, you also have, of course, a finite contact region. So we wanted to make sure that the net lateral force is not still behind the steering axis, but it was actually a little bit in front. But yeah.
All right.
Yeah.
So my second question is about, you showed to us also about this steer active stability control that kind of thing that you put. How it works actually. Can you elaborate more about that?
Yeah. What I can do, I have some more slides on that. I have some more slides on that. Let me find those slides, and then I can talk a little bit about this steer torque controller.
Yes, while waiting for that, maybe others, do you have any question? Other participants, if you would like to have any question, it is good time for you to ask about. We have Professor Arend here. He's really good in bicycle dynamics. He is a subject matter expert in this bicycle dynamics. Maybe you can ask on how to design your own bicycle, maybe, please. Because Prof Arend involved directly with it. Yeah. All right. So we have one. So Dr. Azwe.
Hi, Prof.
Yeah.
In one of your slides, you said that in order to turn right, you have to steer briefly to the left and then let go of the handlebar. Can you explain more why we need that briefly turn to the left?
Yeah, I can explain. So I have to go back to my experiment of the stick on the hand, right? So if the stick falls to one side, what do you do to balance it? You move your hand in that direction, right? So you move the support in the direction of the fall. So if it's falling in this direction, you move your hand in that direction. And if it's falling in the other one, you move your hand. So if the stick falls to the left, you move your hand to the left to get the support underneath, and likewise to the right.
Okay.
With a bicycle, you like to do it. There's the same, right? To balance the whole thing.
Yes.
Where were we? Oh, sorry, I'm on the wrong slide. But with the bicycle, you want to do the same. But let me get to that slide. Yeah. Okay. Now with a bicycle, you like to do the same. So, but how do you move the contact points of a bicycle? I mean, then you have to move the earth, right? Because with the stick, you move your hand, but with a bike. However, in the bike, when you have a steering wheel, and if you move forward and you turn the wheel, then the contact point will go to the left. Or if you steer to the right, it will go to the right. So on a moving bicycle with your steering assembly, you can move your contact points. Okay, now you want to go around the corner. Now to go around the corner, you have to lean into the corner, right? There's no other way. Otherwise, you will fall out. So you have to kill that gravity. The centrifugal and gravity have to be in balance. So you have to lean into the corner. On the bike, how do you get this leaning? I mean, there's nothing you can push against. Nothing. There's only air. Yeah, maybe a neighbor. You can push somebody next to you on the bicycle lane, but that's not nice. So there's nothing you can push against because you have two contact points on the ground. It's a line of contact. You cannot apply a torque. However, if you now steer briefly to the left, your bike will fall over to the right because your contact points go on, and you're in a leaned configuration and you go around the corner. And I really encourage you to do it yourself. So ride on your bike with your open hands, push against the handlebar a little bit with your right hand, and you will see the bike steers to the left briefly, and then it will go to the right. Just do the experiment. That's the best proof.
I'll do it later.
I will make sure that Tazo will do it.
Okay,
Yes.
thank you, Prof.
You're welcome.
All right. So, is there any other question from the participants? Any other question? So let me see. So guys, any other question? So maybe from outside of the university. So we can see a few names here outside of the university. So is there any question to ask Prof. Arend regarding the bicycle design, for example, maybe? I believe nobody would like to ask any question anymore, maybe. So
maybe I can add as well
Yeah,
that if you ever if people in the audience later on think, oh, actually I have a question, don't hesitate to write me. And if you think, but I don't have your number or your email address, you have, because there's one thing you have to type into that thing, and that's my name.
yep.
For me, that's very simple, of course, but for you, it may be a bit difficult. If you type my name, Arend Schwab, if you type that in Google and you hit the first button, you get all the information. My email address, my phone number, my WhatsApp, Zoom, birthday of family, bank account, everything is there. Don't hesitate to contact me.
Yeah, I believe somebody will email it to you after this, because of some of our members here, our participants here, they are also involved in bicycle dynamics, I believe.
Please
So
feel free.
maybe they will send an email
Absolutely.
to you.
Yeah, absolutely.
So it looks like we already covered everything, all the question already answered.
Good.
So Prof. Arend, is there anything else that you wanted to cover before we can wrap up?
No, again, I'm very happy that I was able to get the floor to talk to you, and I hope in the near future to visit you sometime.
All right. So thank you so much. So thank you so much, Prof. Arend. So thank you so much. So and then we also appreciate to all of the participants who able to attend in this webinar. So thank you so much. So before we close our session here, is it possible if everybody can turn on your camera, and then we can take a photo together, maybe using this Google Meet, so we can take a photo together, everybody. So is it?
I will stop presenting then, Ezra.
Yes, no problem. Yes, no problem. So can everybody turn on your camera, and then we can take a photo together?
Yep.
All right. So maybe everybody, Bozetta bike. We have a Bozetta bike here. Cool.
What is that as well?
So there is a company who maybe build up their own bicycle. If I'm not mistaken, maybe Bozetta bike can give some sort of idea what you do actually. Yeah, he or she wrote down there in the chat box. Yeah, hi. So Bozetta bike. Yeah, can we know what is your nature of business actually? Aha.
Okay.
Right. So maybe it is a good start for you to contact
Don't
Prof.
hesitate.
Arend.
Yeah.
Yeah. All right. Maybe that's all for that. We design. Right. So for your information, Prof. Arend, this ISN means that our national sport institution actually.
Cool. Yep.
Yeah. So it is good start.
Yes.
This way, good start. Yeah. So guys, please, we are going to take a photo together. So smile. All right. So done. So that's all for now. So we really appreciate your time, Prof. Arend. I believe you have to wake up. Yeah, you. I know that you wake up.
It's okay. I'm like Aki. I'm early.
Yes. Thank you so much for your time. Thank you so much for your presentation. We are really happy with your presentation. I believe that everybody also feel happy with that. So thank you so much, Prof. Arend.
My pleasure.
So, all participants, thank you so much for attending this webinar. Thank you so much. All right. So
thank you, Prof.
Bye-bye.
Bye.
Bye.